Alright, in this first video on fluids, we're going to define what a fluid is, and then we're going to talk about density and pressure. A lot of this will be familiar to you based on what you've probably already learned in chemistry, but we'll talk about it more now in terms of physics, which will change the variables in the units a little bit. So a fluid is anything that flows, and so the two states of matter we're going to be discussing are both liquids and gases. We'll begin by talking mainly about liquids, and then in the later half of the unit, we'll get more into talking about gases in terms of like thermodynamics and engines and how things like that work. So the first thing we're going to look at is the idea of density. So density, the equation for density is mass per unit volume, or M over V. And a mass is the amount of matter that makes up an object, and in physics we use kilograms. And then volume is the amount of space that matter is taking up. So we typically measure this in liters, which is the SI unit, but in physics we use meters cubed. Don't be confused, these two amounts are not equivalent to one another. If you think about the size of like a 1 liter bottle, it's very small compared to what a meter cubed would be if you think of a meter stick. Those two are not equivalent, and I'll talk about that conversion here in a second. So the something that might look a little bit different to you is the variable that we use for density in physics is this Greek letter rho. It looks like a little cursive fancy p, lowercase p. And the unit that we use then would be kilograms per meter cubed. Typically in chemistry, you're dealing with grams per milliliter because we're looking at really small stuff, or grams per centimeter cubed because you're looking at small amounts of stuff. But in physics, we're using larger units. So the equation then that you'll see is that density, or rho, is equal to mass over volume. Now, to kind of compare, and this really is a value we'll be using a lot, so you should memorize it, is the density of fresh water. So in chemistry, we know that the density, like 1 gram of water is equal to 1 milliliter of water, or 1 centimeter cubed. However, we're not dealing with grams per milliliter. In physics, we're going to look at kilograms per meter cubed. So down here shows that conversion going from grams per milliliter, and we get that the actual density of fresh water that we will use very frequently throughout this unit is 1,000 kilograms in every meter cubed. All right, so pressure is the force that a fluid exerts on an object. So as a gas or liquid come into contact with a surface, the atoms of that fluid, gas, or liquid are striking the container or striking the surface of the object, and that is what causes pressure, is that force. So the actual equation for pressure is the force per unit area, or the total force of the atoms that are being delivered to a specific surface area of the object. So force, we know, is a Newton, and area is meters squared, so the unit is newtons per meter squared, which is actually given a name. It's called a Pascal. Now in chemistry, we deal with atmospheres and millimeters of mercury. We have all these different units for pressure, and I'll talk about them a little bit, but the SI unit that we're going to use for physics should be the Pascal. Alright, so as we stand on the surface of the Earth, you have an entire atmosphere of gas above you, and that pressure that objects experience on the surface of the Earth is called the atmospheric pressure. So that's where the unit of pressure, atmospheres, comes from. So, as we stand on the surface of the Earth, we're experiencing, 1 atmosphere of pressure. So how does that equate to pascals? Well, 1 times 10 to the 5th pascals is 1 atmosphere. Now, to be specific, it's 101,325, which, if you recall, if you've taken chemistry, you might know the conversion factor, 101.3 kilopascals is 1 atmosphere. But for our purposes, we can round it to 1 times 10 to the 5th. So make sure you know this conversion here. And it's important to recognize that we mainly will be dealing with pascals, but we can also deal with atmospheres if our units always just stay the same. So that's just an important thing to check on. All right, so we also can be experiencing a pressure of a fluid, and so one of the sort of easiest examples to think about this is the idea of a scuba diver. So if a scuba diver dives down underneath the surface of the water, there is essentially a big column of water above their head pushing down or exerting a force down on the the cross sectional area of the diver's body. Now, just to sort of envision it, we use this little stick figure, and you're not really, when you're scuba diving, standing up on the bottom of the lake or whatever you're in. But there is a big column of water exerting some pressure on you. And I'm going to derive an equation that will show how that is related and how we actually calculate that. All right, so you have the height of the water column and you have the cross-sectional area of the water column. So if we look at our pressure equation, it's, force per unit area. Well, the force that we'd be talking about here is the weight of the water pushing down on you, and then the area would be like the cross-sectional area of the column that's pushing down on, your head or whatever. Now, if you look here, if we were to change the height of the water column, then that is really what is going to affect the pressure. It's because the cross-sectional area of that column wouldn't change given that the object stayed the same here, right? So it's really only the height that is important in the idea of the pressure of this fluid. So I'm going to now derive an equation using this and using this concept. Right? So let's say we multiply the top and the bottom of this equation by h, which is essentially multiplying by 1, right? If you multiply by h over h. So we get mg, which is the weight of the water, times h. And then we have the volume, or the area on the bottom, times h, which we know if we look at this cylinder, that would be a times h is actually the volume of the water. So we would get mgh over v. And that leaves m over v here, which we just learned that equation. We should be pretty familiar with it, that is actually density. So the pressure that this person is experiencing right here is actually equivalent to rho gh, or density times gravity times the height of the water column. Right? And this type of pressure is called gauge pressure. The reason is because that's what an instrument would read that was submerged under that amount of water. It tells you the pressure that the water is exerting. But that's not the total pressure, because we have to remember that because, the lake or whatever you're in is open to the atmosphere, there's also an atmosphere above you. So the entire pressure, the total pressure, is called the absolute pressure, and that would incorporate the atmospheric pressure. So the atmospheric pressure is usually written with a P sub naught, and it's 1 atmosphere, 1 times 10 to the 5th pascals. So if you wanted to find absolute pressure, you would calculate your gauge pressure and you would add the pressure of the atmosphere to it. All right, in the next video, I'm going to go through several sample problems and give you sort of different images of different devices that are typically used to explain fluid pressure and are used in a lot of different types of problem sets.